Hello, I'm Jeff Ramseyer, and I'm here to talk to you today about continuous credit networks and Layer 2 blockchains. This is joint work with my advisor, Ashish Goel, and we're both at Stanford University. At a high level, blockchains in the modern era build overlay or Layer 2 payment networks as a way of boosting their transaction rate. And these networks, they boost the transaction rate of the overall system, but building them and maintaining them has a real financial cost. And of course, this cost trades off with the performance of the network. Network participants, therefore, would need to understand this trade-off in order to make rational, efficient decisions. So to that end, what we give is a mathematical framework for analyzing the performance of these so-called Layer 2 payment networks. We give reasonably efficient algorithms for computing network performance and for sampling random network configurations. And finally, under certain assumptions, we show that network performance is reasonably well behaved. That is to say, if I invest more money into creating the network, my performance cannot go down. For the rest of this talk, I'll first outline the problem in the cryptocurrency context. Then I'll formalize our network model, and I'll conclude with a summary of our results. So what's the problem? Well, it's well known that most cryptocurrencies get relatively low transaction rates. So for example, the Bitcoin network can handle maybe 5 to 10 transactions per second. Ethereum can handle about twice that. And some other blockchains can do more. But in general, there's usually an order of magnitude or two gap between what blockchains can do and what credit card networks or banking networks can process on a regular basis. And why is this? Well, suppose that one bank wants to send money to another bank. All that the bank has to do is have its computer call up the computer at the other bank and say, send money. And this works because banks have real-world presence, and they're subject to laws, and so if one of them tries to cheat the other electronically, they can sue and reclaim the money. Whereas in the cryptocurrency context, agents are anonymous and can appear and disappear at will. And so no agent can trust any other agent directly. Instead, agents have to trust the network as a whole. And this means that if one agent wants to send money to another, they have to tell the entire network about the transaction, not just their counterparty. And in general, it's much easier to make one computer talk to one other computer than it is to make many computers talk to many other computers at high rate. So it would be really nice if we could somehow replicate this notion of two agents transacting privately in a secure manner in a blockchain. And we can do this to a limited extent. In particular, we can have two agents come together and put money into a joint account. Then they'll trade not money directly, but they'll trade ownership of the funds in the joint account. So for example, here, Agent Owl and Agent Panda have come together and each put $5 into a joint account. So there's $10 in the joint account, and the rest of the blockchain knows about this account. But the Owl and Panda don't have to tell everyone else about which of them owns how much money in the shared account. So for example, when they start, Owl and Panda remember that each owns $5 of the shared $10. But if Owl wants to send money to Panda, it can just update the ownership records, and now Owl will own $4 of the 10, and Panda will own 6. This works fine in practice, and this kind of joint account can be implemented via a reasonably straightforward smart contract. Making it work requires some cryptography, but it suffices to say that at any time, if Owl or Panda wants to close out their joint account, they can take their up till now privately held record of who owns how much money and publish that, and the joint account will pay out, say in this case, $4 to Owl and $6 to Panda. However, there are two problems here. And the first is that creating and maintaining this joint account requires putting capital into escrow. And putting capital down for a long time has a real cost. And second is that this payment channel, while it can handle some transactions privately, it cannot handle all of them. So for example, if Owl keeps sending money to Panda, it will eventually become bankrupt on this channel and won't be able to use this channel to send more money to Panda, at least until Panda starts sending money back to Owl. So that's one channel in a payment network. In general, we could have many agents with many channels between agents. And if one agent wants to pay another and they don't have a direct link, they can route money along paths in the graph, such as if A wants to pay E, A can pay B, who can then pay C, who can then pay D, who can then pay E. For the rest of this talk, we'll call a set of underlying escrow accounts the underlying payment network, and we'll call it a set of ownership records a configuration of the payment network. Sending money through the payment network requires just updating these ownership records, and this takes maybe seconds, and this can happen at high volume. So we'll think of the configuration of a network as changing very rapidly, whereas creating or destroying an escrow account requires publishing a transaction to the public blockchain, which, depending on the blockchain, can take minutes or hours to settle. And so for this talk, we'll think of the network, the underlying payment network, as fixed. In general, no payment network can resolve every possible sequence of transactions. So what we'd like to understand the trade-off again between the cost and the topology of a network and the fraction of transactions that it successfully resolves. So that's the cryptocurrency context. The last thing to formalize about this network model is what do we actually mean by performance? Intuitively, we'd like to capture a notion, roughly speaking, that states, what is the chance that for some transaction, what is the chance that that transaction succeeds in a so-called random network configuration? And there's many ways to define this model, but they all work out to be roughly the same. So consider this simple example. Suppose that I'm doing some online shopping, and while I'm shopping, everyone else is transacting. And from my point of view, everyone else's behavior is something like a random process. And every time somebody else sends money, this configuration of the network changes. So from my point of view, while I'm shopping, the configuration of the network is changing rapidly. And so when I finally finish my shopping and I go to the network and I ask it, hey network, can you send money to the merchant for me right now? The network is essentially in a random configuration. So what I'd like to study is the chance that the network, when I go to actually send money, what's the chance that the network will actually be able to resolve my transaction? Formally, we'll define random as the stationary distribution of a Markov chain, where at every time step we'll draw some random transaction from, say, the real-world distribution of what everyone else is doing, and then we'll execute that transaction if possible. Now, the liquidity of any transaction, of course, depends on that stationary distribution, and that stationary distribution depends on what kind of transactions everyone else is doing. For the rest of this talk, we'll assume that distribution of what everyone else is doing is symmetric. That is to say, I'm as likely to pay someone else as someone else is to pay me. And before I go on, I should mention that this kind of network model has been studied in the literature as what's called a credit network, and it has applications beyond cryptocurrencies. Including things such as trust networks or reputation networks. It was applied as a way of reducing email spam. It comes up in certain online commerce. And so all of our results about cryptocurrencies would apply to these other contexts as well. And it was also studied in the case where every transaction has the same constant size. So that's the formal network model. The last thing to do is summarize our results. And so as I said, we give a reasonably efficient algorithm for computing the liquidity of any given transaction. We show that there's an efficient algorithm for sampling a random network configuration. And finally, under certain assumptions, we show that network performance is monotonic with network cost. So first, we show that liquidity computation reduces to computing electrical resistance. And this means that if you want to compute liquidity, you can use your favorite algorithm for computing electrical resistance. And Algorithms that approximate electrical resistance in very fast time is an active area of research. And so this can be done relatively efficiently. Next, we show that sampling according to the stationary distribution of our Markov chain reduces to sampling from a distribution of a particular convex set in real space. And sampling from a distribution on a convex set is a well-studied problem, and there are many generic methods, such as, say, hit and run. But in fact, our particular convex set has a very nice decomposable structure, and so sampling can actually be done faster than with generic methods such as hit and run. And finally, we show that for small transactions, adding edges to the network does not decrease liquidity. This means that if say, I'm a business operating in a payment network, my competitor can't come along and add edges to the network, and in doing so, hurt my ability to accept payments from customers. At a high level, you can think of these results as a continuous relaxation of prior work. Getting these results requires some new mathematical machinery, but once we have them, we get a more flexible analysis that we really need for cryptocurrency parameter regimes. And as a side effect, this continuous relaxation reveals that the entire problem has a very nice geometric structure. I should also mention that without the continuous relaxation, an analogous monotonicity question reduces to an open problem in matroid theory that's remained unsolved since the mid-90s. So how do we get these results? Well, step one is to make some structural observations about the space of network configurations. And in particular, we'll define a nice equivalence class over different configurations such that the stationary distribution of our Markov chain is uniform over these equivalence classes. Next, we'll map configurations to points in real space in a useful way. And by useful, we mean that sending money or sending a transaction reduces to adding a vector, and every representative of these equivalence classes map to the same point. Then we look at the volume of the image of that map in Rn, and we'll show that that set corresponds to a generating polynomial of the Askeror count graph. The generating polynomial for reference is a very nice polynomial that somehow captures the structure of the underlying graph. And finally, we'll study liquidity and monotonicity by taking derivatives of that nice polynomial. Of these steps, the conceptually interesting one is step 2, which is how we map configurations of a credit network to points in real space in this useful way. So here's a proof by picture. Suppose we have a graph with just one edge. Then our state space turns into this line where sending money from A to B is like moving right, and sending money from B to A is like moving left. If we added a second edge from B to C, since there's no cycles, these two edges operate independently, and so our state space becomes a rectangle, where again, sending money from A to B is like moving right, and sending money from B to C is like moving up. If we add a third edge, now we have a cycle, and so instead of getting a three-dimensional rectangle, what we get is a two-dimensional space like this, which is actually equal to the projection of a three-dimensional cube back down to 2 space. And this is because we need to somehow capture the notion that sending money from A to C directly achieves the same effect as sending money from A to B to C. And it turns out that that notion turns into projecting along a certain direction. And so in general, our state space is like a dimension number of edges hypercube projected down along some very particular direction to dimension number of vertices space. This map also naturally gives a map from transactions to vectors, such that sending a transaction from a given configuration corresponds to adding a particular vector to a particular point. And a transaction fails if and only if adding that transaction would send a point outside of the gray state space. So for example, for this transaction here, adding this transaction will fail exactly in the red outlined region of the state space. Liquidity then becomes a question of studying the volume of this red outlined space. Well, it turns out that the volume of the red failure region is exactly equal to the length of the transaction times the volume of the projection of the entire gray state space in the direction of the transaction vector. This is not the entire story here, but in general, liquidity analysis turns into a question of comparing the volume of a set to the volume of its projection. I'll close by just mentioning that earlier we assumed that the transaction distribution was symmetric. It would be interesting to relax that assumption to, say, doubly stochastic or a general asymmetric transaction distribution. And in these cases, our model will extend and the mathematical framework will extend. And so we can get sampling via generic methods like, say, hit and run. But computing the exact number for liquidity becomes a challenge. I also think it would be interesting to study transaction fees in this kind of a model. In the real world, if I send money on a cryptocurrency payment network, every node that I visit as I'm sending my money is going to charge me a small transaction fee. And I think studying what's an optimal fee structure would be an interesting open problem. Thanks for your time. I'll be here in the Zoom chat afterwards to answer questions.